okay, I copied it from a magazine, Time magazine, 2 years ago. It shows the Google universe. The Google universe today has, of course, involves the mainstream business of Google, but you have pharmaceuticals, you have cars. Who knows Google cars? Who knows Google cars? Google cars, okay, so self-driving cars. But Google, they are interested in space industry. They're interested in energy, power management, smart buildings, all this, okay? And this was the cover of this issue of Time magazine. You see, they are very ambitious. So software companies become global companies today. This is the message. And of course, you have this also from, this was the cover of Economist, okay, 1.5 years ago. And you have other companies that have very serious ambitions, and also this Chinese company Huawei also, they are very present. So just to tell you that software technologies are becoming very important, and software companies have been transformed into system companies, and this is a huge revolution. And these companies now are interested in global problems. Now, let's say a few words about the Internet of Things and this vision. So, what's the idea behind the Internet of Things? I think I have already explained it to you. So, we have billions of smart devices, billions of computers that are deployed everywhere over the planet, and we have the Internet. And the idea is that we can connect data and send them to the cloud. You see up there, I have the cloud, send them to the cloud. And the cloud, by using big data analytics, will provide intelligence, will allow us to predict events and a better management. Let me go through this slide and present some ideas. Of course, smart energy, you have here smart energy. Smart grids. What it means, smart grids? Smart grids means that we will have a distribution grid for energy that will manage power that comes from different sources. So today you can have power from nuclear plants, from solar energy or soft energy plants. You can have from dams, and these sources of energy have different characteristics. So you can combine the fact, for instance, that you have a lot of sun in the south of India some days, to send the produced energy to the north of India or to sell it to other countries. For each continent, there will be a power grid. So just to tell you, I know about the European power grid, there will be a North American power grid. And the idea is that, for instance, if in Europe we have sunny weather in the south, countries, Mediterranean countries, can make offers of energy that they produce, and the transaction is done automatically. Now, this is not a simple problem to solve, to manage energy at the level of a continent, okay? And transactions will be done automatically. You will have many offers, many people demanding energy, and the system will make the transactions, taking the best offer, I mean matching demands and offers according to criteria. The technological problems you have to solve are extremely difficult. I'm not going to discuss these problems here. Then what is anticipated is also smart factories, I'll talk about that, but also smart highways. Already in Europe we have smart highways. So what is a smart highway? You have a highway with special equipment of sensors that monitors the traffic and also send orders to the drivers. For instance, in the case of accident, in the case of problem of weather, okay? Of course, smart cars you have seen already, and we will have probably in the future smart driving cars. And we will have also, smart farms, smart agriculture. The idea is that you have sensors deployed over the fields, especially for countries where you have problems of scarcity of water, and you will provide water to the plants if they need it, okay? You will not have a stupid system that gives periodically drops of water. And then, of course, there are plans to have telehealth, a lot of telehealth systems. Here you see somebody who swallows a pill, and the pill goes through his tube and transmits parameters, temperature, blood pressure, or other parameters of his body to the hospital. Okay, so this is the vision. Now I would like to explain that this vision, IoT vision, has two different phases. One is what we call the human IoT, and the other is the industrial IoT. The human IoT is just an improvement of the internet as we know it today. How we use the internet today, you are a user, and the basic model is what we call client-server model. I need a service, I ask for a service, and I get back something. What we call the industrial Internet of Things is something very, very different. And this is the challenging part of the Internet of Things. It is about building autonomous services, services that are autonomous, where you don't have human in the loop, no human in the loop. Why no human in the loop? Because we want to be as efficient as possible. So this is the hard part of the Internet of Things, and this is what I'm going to talk about. For this part, there is, I should say that the industrial Internet of Things is not reachable today. It's not possible to have autonomous services with existing internet technology. Why? Because currently the internet has two main problems. One is that the problem with security. The internet is not secure enough. The other problem is that when you send a message to somebody, there is no guarantee that the message will reach the destination within a given time bound. So, if you don't have guarantee, then you cannot have autonomous systems, because in autonomous systems you want to have tight control, and this is not possible if you don't have guaranteed times. So these are the two main problems here. And I would like to say that in the US has been established an industrial internet consortium led by a big company like General Electric to study how we can define a different internet, but we have not seen the results so far. Okay, so now let me say a few words about the scientific and technical challenges behind the Internet of Things. I would like to explain to you a concept that is very important, and is design. What it means to design a system, what it means to design something. It's a concept very important to understand. Whenever you build something, you design something. So here I'm giving the example of an easy apple pie, of a pie. So when you design something, you start, what you see on your left is the requirements, the desire. I desire something, I want to have something. And then there is a first step where you have to give a recipe. You have to give a program to say, oh, I want to do this, how I will proceed. So this is a kind of program or the recipe here. And then the other step is that you have now to apply your recipe and to build something, here your pie, and you need ingredients in this case or resources. So it's important to note that these two steps are independent, and for the same recipe, you can have pies of different quality, depending on the quality of the ingredients you choose. So the same applies if you want to build a house, I mean to have a house. You go to a civil engineer, you explain your desires to a civil engineer, the civil engineer will produce a recipe, a blueprint, and then somebody will build the house, okay? And also here the materials will be using can be of different qualities. Now, when we build systems, we proceed in the same manner. We start from requirements, and then we write an application software, and then we choose a hardware platform, and we run the software on the platform. And the same software can run on different platforms. And of course, the key issue is what? Is whether what we get, the system we get, is correct with respect to the requirements. Now I should say here something very important that you understand. In the example, for instance, of the house, we have a theory. We have well-established theory to build houses that will not collapse for centuries. But for systems, we don't have such a theory. Now, why we don't have such a theory? Ask questions. I don't know. I mean, perhaps because computing is a very young discipline and we don't have mature, this is not a mature discipline. But I don't think this is the deep reason. Anyway, I hope you understand the idea of design, okay, building computing systems. That's very important, especially for the Internet of Things. Because in the Internet of Things, you don't write only software, you build systems. We focus on systems. And when you deal with systems, you write the software and you connect the software with the system, with the hardware. And what is very important is the performance. And the performance is defined by the hardware platform. Okay, now I would like to explain the concept of correctness, what it means that we build a system that is correct. Correctness, in fact, means two things. First thing is that the system is trustworthy. Trustworthy means that it will behave as you expect, despite the different problems that may appear, different mishaps that may appear over the life of the system. Hardware failures, because the hardware can fail, okay? The hardware can have aging phenomena, so this is maybe one problem. Design errors. Do you see the difference between a design error and a hardware failure? Who sees the difference between design error and hardware failure? Do you see the difference? Do you see the difference between design error and hardware failure? Who does not see the difference? That's very important. When you are programming, okay, this is an error due to your mind, okay? I mean, this is a mental error, an error of reasoning. You are responsible for that. You are not responsible for hardware failures. And then other mishaps are disturbances from the environment and malevolent actions. So malevolent actions are attacks, cyber security issues, okay? So when I design a system, I have to take care of all this. And at the same time, if I am a good engineer, because if I build a trustworthy system that costs a lot of money, nobody will buy it. So when I am an engineer, I care about building systems of good quality, but at some reasonable cost. And this is, so you have also to take into account optimization requirements to to use the optimal amount of resources to achieve the right performance. And I would like to explain to you that these two types of requirements, trustworthiness and optimization requirements, are antagonistic. Antagonistic means that if you try to have a better trustworthiness, a more trustworthy system, that it will cost more money. So there are many examples that can illustrate this. If you have questions, I can explain. But today, the situation is as follows in systems engineering. We build systems that are critical systems. What is a critical system? A critical system is a system such that if it fails, a failure will cost a lot of money, may cost human lives. So we should be very careful when we design critical systems. And I would like to say that today we design critical systems that are of low complexity, and okay, their development costs a lot of money. And then we develop very, very, very large systems that are best effort. What it means best effort? When we design them, we try to manage in the best possible way the resources. Typically, a web platform is best effort. Of course, we care about safety and security because this determines the availability of the system. So the availability of the system should not be below a certain threshold, because otherwise the user will be discouraged, disappointed. But okay, in best effort systems we care about resource management mainly. And then you have something intermediate, mission critical systems. In fact, we have 7 levels of criticality between critical, absolutely critical systems and best effort systems. So what's the difference in all this? The difference is these numbers. What is 10 to the minus 9? 10 to the minus 9 is the reliability of a civilian aircraft, of an Airbus or a Boeing that you take to travel. 10 to the minus 9 failures per hour. So 10 to the 1 over 1 billion probability that you have a failure when you fly. And you should note that even with a single failure, the aircraft, okay, can overcome. 10 to the minus 6 is typically the reliability of a networking infrastructure, of a data center, or of a rocket. And 10 to the minus 4 for best effort. Now, why for rockets, for instance, that take human astronauts, we have a reliability 10 to the minus 6 only? Because if we try to multiply by 10 the reliability of a rocket, the cost will increase by 1,000 or more, okay? So what you should understand is that every time we try to increase the reliability of a system, it costs a lot of money. And so for autonomous systems, we have today a lot of problems. Many of them are reported in the press, and others are not reported in the press. And I should say that security is a very, very important issue. We don't know how to guarantee the security of the systems we have. And recently, January 4 this year, you see this news that says that industry responds to CPU security vulnerability. In fact, we know that almost all the Intel processors have a serious security flaw. And of course, Intel says security bug not specific to its processors. So every day we discover security flaws. Why I'm saying this? Because today, under this state of the art, we don't know how to build the industrial Internet of Things, because we cannot guarantee the security of the Internet infrastructure. This is one message you should keep in mind. how much difficult it is to make things, to make systems much more secure. Here, this is a diagram provided by the American, by DARPA, that is the American agency that funds most of the military research in the United States. I will not show you this. Okay, let me show you the other. It studies the evolution of the costs of systems that are dependable, that are trustworthy, like avionic systems. And it shows that as the complexity of the systems grows, the development costs increase exponentially. And here, this slide says that by year 2070, to buy just an aircraft, you will need the defense budget of the United States. So the news are very bad from a technical point of view, and this is something I would like to explain. So I don't know how much time I have, but you know that today we have requirements, very strong requirements for autonomy in the Internet of Things. And the problems are poor trustworthiness, as I said, impossibility to guarantee response times. Also, another problem is that we want to integrate, to make cooperate services that are critical and less critical services. Let me give you an example. You are using your mobile phone to access sensitive data. For instance, records, I mean, sensitive data can be your bank account or some health records. And now, as your mobile phone is not well protected, some intruder may have access to sensitive data if the networking infrastructure is not protected also, and is not guaranteed. Also, another requirement that we have today is that we want all the devices to be updated, the functionality is defined by software, and we want to have software updates. This is something very, very dangerous. Who knows Tesla cars? Tesla cars. Who has heard about Tesla cars? So Tesla cars are cars with autonomous features. And you know, Tesla, they make software updates every week. Every week they change the software. This is very, very bad practice from a classical, I mean, standard point engineer, from a standard engineering point of view. Because this we will never do with aircraft. I have worked a lot with the aircraft industry. When you certify an aircraft, so Boeing or Airbus, they certify an aircraft. These are typically critical systems, but also self-driving cars are critical systems. When you certify an aircraft, you cannot modify the software. Not only you cannot modify the software, but you buy all the hardware for 50 years. So you buy the hardware for 50 years because you will be using the same technology that has been certified. You don't accept to change the hardware. So these are practices that are very dangerous in my opinion. Now, I would like to say that this is the situation today. I'm not very optimistic about the future. Some people are more optimistic than me. For instance, Elon Musk, who is the CEO of Tesla, say that I really consider autonomous driving a solved problem. I don't believe this. And this is the position of Google. So the person who writes this article in ACM journal is Winter Cerf, a guy I know very well. And he says that security problems will remain forever as we have health problems, okay? He says our machines are infected and they are sometimes also contagious. Our reactions in the public health world involve inoculation and quarantine, and we tolerate this because we recognize our health is at risk if other members of society fail to protect, etc. Sadly, Virus detection seems to be closing the barn door after the horses have left, to mangle the metaphor. So you see that the guy says that this is something that we should live with, like illness. You cannot eradicate illness. So this is a bad position by Google. Okay, my position now is that we researchers, we should try to understand the limitations and identify relevant research avenues. I don't have time to explain why classical systems engineering should be adapted somehow, and in particular to take into account breakthroughs in artificial intelligence. Okay, something else I have already explained is that we don't design computing systems as we build bridges. When we build a bridge, we have theory, you write down systems of differential equations, and you have what we call predictability. You can predict what will happen. And for computing systems, unfortunately, we don't have such theory. This is a set of slides that is a bit large, so I skip something. Okay, so here I'm explaining why the current state of the art is not good enough. And let me talk about two important trends in systems engineering, and then I will stop. One trend is that we will be building systems. Systems will be designed as cyberphysical systems. And I would like to explain what is a cyberphysical system. We have different systems are built from components, from bricks. And we have different types of components. We have simple components and more complex components. A component can be a function. A function is a box. You give A and computes f of a. You understand what is a function, and a program typically computes a function. Now, you can have components that are streamers. What is a streamer? A streamer does not receive a single value. It receives a stream of values, and it produces at the output a stream of values. Then we have what I explained, embedded system. So we have a computer, and the computer continuously interacts with the external environment because it controls a physical process. You see, the streamer, it receives values, it produces output, but you have no closed loop. So in the embedded system, you have closed loop. And then we have what we call now cyberphysical components, and most systems will be built using cyberphysical components, where inside the component I have an embedded system and its environment, an electromechanical environment. Imagine that you want to build the arm of a robot. So the arm of a robot will have electromechanical pieces, and each piece will have also computers, okay? So each component will be a cyberphysical component. But let me explain the idea of cyberphysical systems from a different angle of attack. Who knows what is 3D printing? 3D printing. What? 3D printing, you know? 3D printing? 3D printing? So 3D printer, I build a model, a geometric model of an object, and then I send it to a printer, and for instance, the model of this bot, and you send it to the printer and it will build this bot, okay? Now here you see a motorcycle that has been 3D printed. So a motorcycle is, oh, there is a problem? No? Okay. So a motorcycle is an object that is complex. You have to give the geometric dimensions, of course, but you give also you have tools now, you give the strength of the material from which it is made, and the tool, before producing the motorcycle, we build a virtual model of the motorcycle. You can drive it, you can test it, and then you can send it not to a 3D printer, but to a factory. to a factory to produce this object. Okay, and this is a very interesting idea. You can apply it today to different types of objects, of engines. So for instance, I want to design an engine here that has pistons, has a shaft. I give not only the geometric dimensions of the objects, but also I give the properties of the materials I will be using. I have sensors also, and I have a program that will build the virtual model of the engine. I run the engine and I test it. So in the future, it will be possible for you to design your own car. How it will be possible to design your own car? You go to the website of a car company, say Daimler, and you have libraries of components. So you choose different components, and you have a tool also that you find in the cloud, and you compose the components, and you build your car. Now, when you compose your components, the tool will build a model of the car, and you can run your car, and if you are happy with this, you like it, he will give you how much it costs. It costs so many rupees. You send a check to the manufacturer, and you get back your car. Okay, that's a great idea because this opens the way to creativity. You will be the creator of the objects you have at house. If you can create cars, you can create furniture, you can create different types of appliances, etc. Of course, in order to achieve this, you need to solve, and I don't know what's your level exactly, to solve systems of differential, to integrate systems of differential equations, very complex systems with discrete events. This raises a very, very hard problems we don't know how to solve, and I'm not going to discuss this here. Okay, so let me jump to intelligence to say a few words about what intelligence means for the Internet of Things, for systems engineering. A key idea today is that in the IoT, we will have intelligence. It will be possible to handle knowledge and solve problems automatically. What is knowledge? It's important to understand what is knowledge. It's a very basic concept. If you understand what is information. Knowledge is information that you can use either to understand the situation or to solve a problem. So knowledge is not simple information. Simple information is today the temperature is 28 degrees. This is simple information. But knowledge is information that you can use and reuse. So the Pythagorean theorem is knowledge. You know the Pythagorean theorem? Who knows the Pythagorean theorem here? The Pythagorean theorem? Who knows the Pythagorean theorem? Come on. Or perhaps I'm pronouncing in the wrong manner, but the Pythagorean theorem okay, they all know the Pythagorean. So the Pythagorean theorem is knowledge. Why it is knowledge? Because you can use it to solve other problems, okay? What is knowledge? Knowledge is an algorithm that you know. Newton's laws are knowledge, okay? So knowledge is important. You know that knowledge, today we can extract it also by doing data analytics. So in the future, the dream is that we will have in the cloud, digital knowledge that we extract by applying data analytics, learning techniques, statistical inference, and we'll have also scientific knowledge or mathematical knowledge. And the dream is that we will have machines now that will understand our requests. So instead of doing searches by using keywords, you will say, for instance, I am in Mangalore and I would like to visit forests with red trees. Okay, so this is your request. Then this is treated by the machine, and the machine will combine different services to give you an answer. And the answer will be an interactive menu to say, well, there are so many solutions, and for each solution, it will combine different services. It will combine Google Maps, it will combine meteorological services, it will combine many, many services, okay? And it will guide you to solve your problem. Okay, I mean, I'm taking a simple problem, it can be an economical problem or whatever. So this is knowledge-based engineering. For the moment, we are far from having a semantic web because we don't have machines that understand quite well what we are doing. The other way we will be using intelligence in IoT is adaptivity. What means adaptivity? Adaptivity means that we will have systems that will adapt their behavior to cope with uncertainty. And here I have a figure that probably will explain this. So, as we know that we cannot design systems that are flawless. So I think we will give up this idea to design systems today. Aircraft systems are completely flawless. But the systems we will have on self-driving cars, for sure, they will not be flawless. And if you have questions, I can explain why they cannot be flawless. Now, even if you have a system that can have problems, can have some flaws, some problems may appear, you can imagine that you have a controller which is called an adaptive controller. What does an adaptive controller? The adaptive controller is an intelligent controller that monitors the state of the system, and depending on what it sees, it happens, it reacts and mitigates. If something wrong happens, it mitigates. Consider, for instance, that this wrong is, say, an attack. If an attack occurs in the system, then it will act on the system to mitigate the effect of the attack, or will organize some counter measures against the invader, whatever. Okay, now how works an adaptive controller? It combines two functions. It works like our mind. It combines objective management, so it has many different objectives. And for each objective, if it chooses an objective, the planner, the corresponding planner is activated about how to reach the objective, and then the learning function works. I have this. So this is the way it works an adaptive controller, like our mind. So in our mind, we combines three functions. The most important function is the one in the middle, that is management of objectives. So the objectives are determined by our desires. So let me consider a simple case. So some evening, I am at home, and I'm saying what I will be doing tonight. Okay, so I examine my desires and say, maybe I go to the stadium, I go to see a movie, or I go to a restaurant. So these are three possible objectives depending on my desires. Now, the object management evaluator will run and will choose one based on various criteria I have, okay? So I have a model, as I said in my lecture yesterday, I have a model of the external world, and then, okay, I can evaluate, and I pick one, and as I like soccer, I decide to go for soccer this night. Now, the planner will say how I will do that to go from home to the stadium. And then, once I had this experience, the learning function will learn and will say perhaps, oh, it was not a good idea to go tonight to the stadium. Okay, so what does the learning function here? The learning function learns and modifies some parameters that the parameters are involved in the objective management model. So it will change your preferences in the objective management model. Okay, so this is the idea of adaptivity. It's a very, very important idea, and this is already applied in networks, in data mining systems, in many applications. Okay, you don't see them, but of course, the problem is how to have adaptive controllers that are fast enough, because sometimes learning and the management of objectives is a hard problem, is an optimization problem, and you need a lot of time to decide this, and decisions should be taken sometimes urgently, and the response times are very important. So I think I'm about to finish now. So where are we standing today? The Internet of Things is something great. We have plenty of smart objects, and they are interconnected. So the challenge is how and their number is increasing. Here you see that by 2020 we will have 25 billion objects, interconnected objects. Then the question is how far we are from the emergence of the real Internet of Things. And here there is this is the so-called hype curve that is produced by a technological company, by an expert company, Gartner, which is a famous expert company. And this curve plots the expectations. So you have, and the y-axis, the expectations, and the x-axis, you have, as you move from left, from the origin to right, the maturity of a technology increases. So what this shows is that, I don't know whether I can show, no, I cannot show here. So when a technology is young, very young, the expectations are very low, and then the expectations increase, and people are putting money on this technology in particular, and but still the technology is not adopted. So the technology comes to a peak of expectations, and then the expectations, you have a point of disappointment sometime, and the expectations go down, and probably the technology will reach some productivity plateau later. Now, I don't know whether you can read here the Internet, oops, sorry. So the Internet of Things is standing up there. It's underscored in red here. So it's the highest of expectations in July 14, and the situation is, okay, you cannot read this. So I have all of these curves until July 17. It's very high. I mean, the hype is still very, very high. Now, to say something else, why the Internet of Things for the moment is not yet a vision that is, say, for the next 10 years. Because there is another problem, that is the integration of the networking infrastructure. Here in this diagram, you see that we have a big variety of networks. You have the range versus the data rate. I don't know whether this is visible from there. And you have a body area network, person area network, local networks, wide area networks, and the data rate. So normally there should be some agreement about how to interconnect these networks that have very different characteristics. And I should say that the big companies do not agree or do not want to agree on a solution about that. Why? Because telecommunication companies would like that everything is done by using telecommunication networks, and internet companies privilege internet solutions. So this is also a problem. Okay, I think I stop here, and I will take questions, and I hope we will have an interesting discussion. Thank you very much for your attention. Thank you.